Today I will talk about orifice meter. Now what is the application of orifice meter? The orifice meter is used to measure the discharge, means rate of fluid flow or volumetric flow rate through a pipe. Now what is the principle behind it and principle behind orifice meter? The orifice meter operates on the same principle as the Venturi meter. So what is the working principle of Venturi meter? So Venturi meter works on that Bernoulli's principle. Here also I will use Bernoulli's principle to calculate volumetric flow rate. Now what is the orifice meter? Orifice meter is a circular thin metal plate with a small hole in its center that is placed in the pipeline between two flanges called orifice flange. The plane of the orifice plate is perpendicular to the axis of the pipe and the hole is concentric with the pipe. Now here, so this is the orifice plate and this is perpendicular to the that axis of the pipe and it is a concentric with the pipe. Now as the fluid flows through the orifice, the area, so when that fluid is flowing through that orifice, so there will be one area where that flow area is minimum and velocity is maximum. This area is called vena contacta. So this is very important. What is vena contacta? Now next, first consider an orifice meter fitted in horizontal pipe through which a fluid is flowing. So capital D is the diameter of the pipe. So this is the capital D, diameter of the pipe, and then small d, diameter of the orifice. So this is the diameter of the orifice, means whole diameter, that orifice hole. So that whole diameter is D, and DC, this is the diameter of vena contacta. So this is the diameter of vena contacta. Now if I calculate the cross sectional area, obviously pi by 4 the disc, so that is the area of the pipe, pi by 4 small disc, so that cross sectional area of the orifice, and AC is the cross sectional area of the vena contacta, so pi by 4 by DC square. Now if you consider that point here and point here, so P1, V1 and Z1 is the pressure, velocity and datum height at the section 1, and P2, V2 and Z2 is the corresponding value at section 2, means P2 is pressure, V2 is velocity and Z2 is the datum head at the section 2. Now first some coefficient, hydraulic coefficient of the orifice meter. So remember coefficient of the velocity, so CV is the ratio of actual velocity of the jet at the vena contacta to the theoretical velocity. So that V actual by V theoretical. Remember this only. Later we will talk about that. Then CV actually lies between 0.95 to 0.99. Next is coefficient of contraction. Now it is defined as the ratio of cross sectional area of the jet at the vena contacta to the cross sectional area of the orifice, because we don't know which position that vena contacta will form. So that from this coefficient we can modify the equation. So CC is here AC by the capital A. So pi DC square by pi D square by 4, here pi DC square by 4, pi D square by 4. So DC by D whole square. So CC actually lies between 0.61 to 0.61. Average value is 0.64. Now based on that, another is coefficient of discharge. So that coefficient of discharge CD is nothing but that theoretical discharge, that orifice discharge to the theoretical discharge. So this is orifice discharge by theoretical. So that is CC into CV. So remember that CD is equal to CC into CV. That is important. And CD lies between 0.6 to 0.65, means orifice coefficient. What is the value of orifice coefficient? So remember it is lies between 0.62 to 0.65. Next, again apply the Bernoulli's equation like Venturi meter. So here section 1 and section 2. So applying Bernoulli's equation, so P1 by rho g, V1 square by 2g plus Z1 is equal to P2 by rho g plus P2 square by 2g plus Z2. So here that orifice meter is in that horizontal position, so Z1 is equal to Z2. So P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g. So this equation become this equation. Now so if I consider that P1 by rho g and minus P2 by rho g is nothing but H. So we can write, so that is H. if I that pressure difference here and here, that P1 by rho g minus P2 by rho g is that H. So we can write that here if I reorganize, so that is P1 by rho g minus P2 by rho g, so that is H. So from here we can write V2 square minus V1 square is nothing but 2gh. So that you have to remember. Now using the continuity equation, we know that continuity equation A1 into V1 or A into V, area into velocity. So Q is equal to A1 into V1 is equal to AC into V2. So this position volumetric flow rate and this position volumetric flow rate are same. So we can write A V1 is equal to AC V2. So from that V1 we can write Q by A, V2 we can write Q by AC. Now plugging here this equation. So V2 Q by AC square minus Q by S whole square is equal to 2gh. So from that if I that make common Q square, so 1 by AC square minus 1 by A square is equal to 2gh. Now if I do that simplification, so we will get that theoretical discharge Q is nothing but root over of 2gh A capital S square AC square by A square minus AC square. So that is the theoretical discharge. Now we will work on the coefficient. Now here Q actual, so Q theoretical we got. Now Q you know that CD is that Q actual by Q theoretical. So Q actual will be CD into that Q theoretical. So now that is CD into root over of 2gh A square into AC square by A square minus AC square. Okay, so we know that CD Q actual by Q theoretical. So we got the Q actual. Now that the theoretical velocity, we know theoretical velocity at section 2. So V2 is nothing but A root over of 2gh root over of A2 square minus A square. So now we know that here that Q theoretical velocity theoretical discharge. So from here we can easily calculate the what will be the V2. V2 is nothing but what? Q by SC. So from that we can easily calculate what will be the V2. So V2 is A root over 2gh by root over of A square minus A square, that A square. So that we can calculate. So that is not A square, AC square. Now here that coefficient of contraction, so that CC is equal to AC by A. So real fluid AC is equal to that CC into that A. So we know we can easily calculate that AC. Now substituting AC is equal to CC into A into the equation. So we will get, so V1 is equal to, so we know that V1 is equal to Q by A. So now here and Q we know what? Q we know that A into AC into V2 by A. So now here AC we know that is CC into A. So V1 is equal to CC into A, CC into A into V2 by A. So from that we can get V1. Now here again on pressure difference, we know pressure difference and head loss. So H is equal to, we got that right here. This is that V2 square minus V1 square is equal to 2gh. So V2 we go now, V1 we know. So from here, so H we can easily get V2 square by 2g minus CC square minus S square V2 square by S square by 2g. So from that we can calculate H. Okay, and H, so here we are calculating V2. So 2gh is equal to V2 square 1 minus CC square minus S square by capital S square. So V2 square is equal to 2gh A capital S square A capital S square minus CC square S square. So ultimately we got that V2 is nothing but A root over of 2gh that A square minus CC square into A square. That we got V2. Now CV is nothing but V2 actual by V2 theoretical. So we can plugging that value. So here we can get that CV is nothing but root over of A S capital S square minus small s square divided by under root a square minus cc square minus a square. So from here we get CV. Now CD is nothing but CC into CV. So CD into CC into CV. CV is this term. Okay, so we'll get how to calculate the CD. So if we know the CC and if we know all these parameter, we can easily calculate that CD. So after getting CD, so we know the discharge that Q is nothing but AC into V2. So that AC we know CC into A. So Q will be CC into A into V2. So V2 we already know. Okay, so from that we'll get that Q is equal to CD. Now CC into C, A we know that here from here we know that CC is AC is equal to CC into A. So from here we can plug that and we'll get that Q is equal to CD into small a into capital A into root of 2gh a square capital A square minus a square. So ultimately Q is nothing but the CD into A into capital A root 2gh root over of a square minus a square. So this is the discharge with coefficient of discharge. So that we got. So this is the discharge through orifice meter. Means from if we use this formula, we can easily calculate what will be the discharge. Now, so here H actually can be modified because we are calculating pressure difference using that U2 manometer. So H will be X into so here if the differential U2 manometer contains a liquid which is heavier than the liquid flowing through the pipe, then H will be X into X is actually that height difference, that rho manometer by rho pipe minus 1. So here rho manometer will greater than rho pipe. So from here, so we know that H is equal to P1 by rho G minus P2 by rho G. So here P mano means density of the heavier liquid used in U2 manometer. Rho pipe means density of the liquid flowing through the pipe, and X is the difference of the heavier liquid column in the U2 manometer. So now from here we can easily know that H is equal to X into rho Hg by rho H2 if we consider that manometer liquid is mercury and that fluid which is flowing through a pipe, so that is water, this is minor. Now if I plug all these values, so H will be nothing but 12.6x. So if we know the X for H will be 12.6 into X. So based on that we can easily calculate H, and then we can plug that original formula, then we can easily calculate what will be the discharge. I think that's it. Thank you.